So in this video, I introduce spanning sets and linear dependence of vectors. In order to begin this, we need to quickly review what we mean by a linear combination. So we say a vector B is a linear combination of R other vectors, v1, v2 up to vr, if there are scalars, c1, c2 up to cr, so that the particular sum of products, c1 times v1 plus c2 times v2, plus up to cr times vr, that sum of scalar multiples of vectors is equal to the vector B. Now, so just as an example, the vector 3, 2, 7 is a linear combination of the vectors 1, 0, 1 and 0, 1, 2, because you can find scalars, in this case 3 and 2, so that 3 times v1 plus 2 times v2 is equal to the vector B. So let's look at an example. I want to know, is the vector 1, 2, 3 a linear combination of the two vectors 1, 0, 3 and negative 1, 1 and negative 3? To answer that question, I just need to see, can I find any two scalars so that the sum of scalar multiples of those vectors on the left is equal to my target vector 1, 2, 3? Well, the left-hand side is just a sum of vectors, so collapse that to be one vector by just adding up everything and distributing the scalar through the different vectors. Once you do that, you can then compare the vector on the left with the vector on the right, and if they are indeed equal, that means their components are equal. That would then lead to these equations. I think it's pretty obvious to see how to go from one step to the other. From here, we could then look at the corresponding augmented matrix. Now the question is, are there scalars where this is true? If there are scalars where the system has a solution, that means that this augmented matrix must correspond to a consistent system. So to answer that, to find out if a system is consistent, it's pretty easy. You just go and take the augmented matrix form and just row reduce it. And then just by looking at that, you can see that there is no leading entry in the constant column. Therefore, the corresponding system must be consistent. So the answer is yes. 1, 2, 3 is a linear combination of these two other vectors. Now, if you want to go further and find out what actually is the linear combination that does the job, you have to then go a step further and give a solution to the system. Any solution will work. So in this case, one solution is C1 is 3 and C2 is 2. And if you just check it, that's correct. Now let's just notice, though, that by doing so, when I did this work, when I formed the first linear combination, the columns of the left-hand side of that coefficient matrix are the vectors forming the linear combination, and the last column in the augmented matrix is actually the vector that we're trying to find out if it's a linear combination of the others. So it's the exact same two vectors. All I did was change my target vector to be 2, 3, 4. So once again, I want to know, is 2, 3, 4 a linear combination of those other two vectors? To do so, it's pretty easy. We just repeat the steps I just did. I want to know, are there scalars C1 and C2 so that this particular algebraic statement is true? That can only be true if this linear system has a solution. To find that out, we look at the augmented matrix. We then row reduce it. Notice, though, that now there is a leading entry in the constant column. That means if you take this augmented system, this augmented matrix, and write it back as a system in terms of C1 and C2, you'll get the equation, in this case, 0 equals 1. It's clearly false. There is no solution. That means then this vector 2, 3, 4 is just not a linear combination of the other two vectors. You cannot ever find those two constants. Now, once again, though, notice that when you did this work, did you see how the vectors form the columns of the corresponding coefficient matrix, while the last column in the augmented matrix is actually our target vector? This happens so often, in fact, happens every single time we do this process. It deserves a theorem. So, this is called theorem 2.4 actually in your book. We're going to refer to it quite a bit. A linear system with an augmented matrix A-B, or A with adjoined B, is consistent if and only if B is a linear combination of the columns of A. And actually, if it actually is consistent, then any solution to the corresponding system using the variable c1, c2 up to cn will provide the coefficients for that linear combination. So there's this nice way to hop between all of these different ideas. When you have a linear system, you can look at it instead as an augmented matrix, but then also now you can look at it in terms of a linear combination of the columns being equal to the constant vector. These are all related to each other. Now we have hopefully a fairly good understanding of equations of lines in 2 or 3 space and equations of planes in either 2 or 3 space. So let's look at the plane again. So then the equation of a plane in vector form passing through the origin, so the vector p is the 0 vector, is x equals a scalar s times v1 plus the scalar t times v2. As an example, I have one here on the screen. Now, when you look at the right-hand side, since s and t can be any scalars right now, because that describes all the points in the plane, the right-hand side is looking at all possible linear combinations of 2 vectors, 1, 1, and 2, 0. Again, the right-hand side of that equation is just actually saying, look at all possible linear combinations of those 2 vectors. Now, geometrically, these 2 vectors make like their own coordinate system in the plane. It's almost as if every single point in the plane can be written as a certain linear combination of the vectors 1, 1, and 2, 0. So what we want to do is then to generalize this idea, because that sounds useful, that I can represent points in a plane as a set of all possible linear combinations where I get to set the vectors that do it. That sounds kind of nice. So we can. It's just that we have to use potentially more vectors and also potentially higher dimensions. So if S is a set of vectors, v1 through vk, and they're all from Rn, so that means that they could have n components, then the set of all possible linear combinations of those vectors is called the span of those vectors, is denoted the span of v1 up to vk. And sometimes if you already went through the trouble of saying the set S is that set of vectors, you can just say the span of S. If V is some collection of vectors in Rn, so the span of S is that set of vectors, we then say S is a spanning set for that set of vectors. So understanding what the span creates is going to take time. A good idea to have in your head is a span is sort of a generalization of the plane, where you don't have one direction or 2 directions like you do in a plane, but you have many directions, all making different axes, and it all lies inside some ambient space. So in order to get you a better feeling for how to describe what a span is, let's just figure out if a certain vector is in a span. So this is just a matter of looking at the definition. I want to know, is the vector 1, 1 in the span of these 3 vectors? To do so, that just means, is there a linear combination of those vectors that adds up to 1, 1? We don't care how many linear combinations are possible. We just want to know, is there one such linear combination? So, but by our theorem though, if that's true, all we have to do is to find out if the augmented matrix, whose last column is the target vector and the columns of the vectors I'm using in the linear combination, is the corresponding system consistent. If it is consistent, then there is a linear combination of these vectors that adds up to 1, 1, and that means then 1, 1 is in the span. So let's just go ahead and find out, is that system consistent? To do so, we just row reduce it. You can now see that the constant column does not have a leading 1. Because of that, there is a solution, because that system is consistent. So yes, yeah, that vector is in the span. But if you want to go a step further, I know it's in the span. That means it is a linear combination. That means that I can figure out one such linear combination that adds up to 1, 1. To do that, I actually have to go through the process of solving the system, which I've done all the work, really. I just have to look at what is the corresponding system using the constants C1, C2, C3. And then notice here that C3 would be free. I can make it be anything I want. So then I'll choose it to be 0. And that gives me the other scalars being C1 is -1 and C2 is 1. And that gives me the linear combination. That's the linear combination of the three vectors that adds up to 1, 1. So yeah, 1, 1 is in the span of those vectors. Easy, right? So I want to know, once again, is this vector in the span of these three vectors? Notice I've gone up a dimension. That doesn't actually matter. It doesn't hurt anything. The process is exactly the same. To find out if that vector is in the span, I just want to know, is there a linear combination of these vectors in S that equals 1, 1, 3, 4? So that means then, by our theorem though, that means that the corresponding system that has this augmented matrix has to be consistent. So let's go ahead and just find out if it's consistent. When you row reduce it, you notice though that there is a leading entry in the constant column. So if you try going back to the system in terms of C1, C2, and C3, you'll get the equation in this case of 0 equals 1. That's impossible. So there's no way to do it. In this case, no. This vector is not in the span because of that very last row. All right, so let's increase the difficulty a little bit. This time, I don't want to know is a particular vector in the span. I want to describe all the vectors in the span. To do that, it's not difficult. It's pretty much the exact same thing we just did, with just some more symbols. But there is a small little nuance. Also notice that, once again, the number of entries in the vector is 4. That doesn't actually matter. As long as they're all the same, this process works. I'm doing that because I'm trying to show you that the actual number of components, the number of coordinates of the vector, don't really matter. So first, let's pretend that we have some generic vector in the span. Now, if it's generic, I don't know what their coordinates are, so we'll call that vector x, y, z, w. Yeah, I know, I probably should have called it w, x, y, z, but I didn't. So let's just move on. Then this vector, if it actually is in the span, it's got to be a linear combination of those three vectors. But that means, by our best friend, Theorem 2.4, that this augmented matrix, the corresponding system, has but got to be consistent. That means if we row reduce it, that there can't be a leading one in the constant column, or a leading entry at least in the constant column. So here we want to row reduce this. This is one of those times where some calculators can't handle it because it can't do variables. Some can. Some, though, you can just type into a computer like Wolfram Alpha or Maple or Mathematica or MATLAB, or there's lots of other things that can just do this for you. This is probably one of those times when you want to do the row reduction yourself by hand. So if you do, you get that thing. That's the row reduced echelon form. If you were really careful. Notice I didn't divide by the very last entry to get a 1 there, because I don't know if that very last equation in the constant column in the last row, if that actually is a number that's non-zero, so I can't divide by it. That's why it's dangerous to let a computer do it, because it doesn't know any better, and it tends to just sort of pretend everything is not 0 and just cancel things. So let's see. We know that this system has to be consistent because the vector x, y, z is in the span. Well, the only way that's true is there can't be a leading entry in the constant column. That means that one equation, x minus 2y minus 3z plus w, can't be a non-zero number. It's got to be 0. If it's not 0, there will be a leading entry there. So that means the system is consistent if this equation, x minus 2y minus 3z plus w, is 0. Therefore, the span is the set of all vectors where that equation is true. That's it. That's how that problem is done. Now, let's go ahead and make it be a little bit more interesting. This time, I wanted to show you that the span of two vectors actually isn't just some arbitrary thing. It's actually all of R2. It's the plane. Now, why is that true? Hopefully obvious to you, the span of those two vectors certainly can't be anything more than R2, because you're only adding vectors that are in R2 to each other. So then you can't become more than that space. You're always trapped inside of it. All we have to do then to show that R2 is the span of those two vectors is that every single vector in R2 is in the span. So, to do so, very similar to what we just did, I'm going to show that every single vector x comma y is in the span of those two vectors. In other words, I'm going to show that x comma y is a linear combination of those two vectors. To do that, by theorem 2.4, look at the corresponding augmented matrix and the system where the vectors are the columns for the constant coefficient, the constant matrix, the coefficient matrix. And the right-hand side is just the target vector, x comma y. If x comma y is a linear combination of those two vectors, the corresponding system has got to be consistent. Let's just row reduce it and see what happens. So again, one of those times you probably should do this by hand and not like a computer do it or like a calculator do it. You probably should do the row operations by hand. You'll then get this. Now I stopped after a certain point. I could keep going here, but this is as far as I need to go really, because I now know by looking at that matrix that is in row echelon form. As it's row echelon form, I instantly know that the number of leading entries in this case is 2, and that's the number of rows. So then this system is instantly consistent, which means then every vector is a linear combination of just these two. But, so I could stop here if I want, but I want to go a little further for you. So then I continue with the row operations to get the RREF form of that matrix. Notice you get some pretty nasty coefficients. This system is always consistent, and so therefore x comma y is always in the span. But if you want to know what the actual linear combination is that adds up to the vector x comma y, I have to solve the corresponding system. And in that case, the corresponding system is C1 is y plus x over 3, and C2 is y minus 2x divided by 3. And you can check the linear combination you like. This particular linear combination of these two vectors will add up to the vector x comma y. So R2 in fact is the span of the vectors 1, 2 and -1, 1. Now, one last thing. This one we won't even discuss in deep detail. I want to know, is R2 the span of E1 and E2? Well, it's pretty easy to do so. I'm going to do the same argument I did before. If you want to show two sets are equal, you show that every element of one is an element of the other and vice versa. So the vectors E1 and E2 are vectors in R2. So then every single linear combination of those two vectors are in R2. The next question then is every vector in R2 a linear combination of E1 and E2? Well, yeah, because E1 just makes the x-axis. E2 just makes the y-axis. So then every single vector is a linear combination of those two. For example, the vector 2, 3 is the vector 2e1 plus 3e2. So then, yeah, this is actually really trivial to do and to understand. You can even extend this out if you like. Rn is then the span of e1, e2 up to en. So I've already gone through and shown you how that in one case, two vectors span all of R2. And in another case, I gave you 3 vectors, and I wanted to know a way to describe the span using an algebraic equation, and I showed you how to do that. Thing is, though, there's at least one pretty obvious example which started this whole argument, which you really should be very clear on. So let's suppose that you look at the span of just 2 vectors. Those 2 vectors point in different directions, that they're not multiples of each other. I want to give you a vector form to describe that span, and I want to talk about what it means geometrically. So in vector form, I mean, the span is just the set of all possible linear combinations. So the vector that's in the span, called x, which is the vector x comma y, z, is just any possible linear combination of those 2 vectors. Now normally, up to this point, I've been calling these scalars C1 and C2, but let's just not and call it S and T. That equation then is a vector way of finding or describing the span of those 2 vectors. But when you write it that way, isn't it pretty obvious? That's the equation of a plane. So that's just a plane. So if you have 2 vectors in R3 that point in different directions, and you want to know what's the span, it's just a plane. The same is true in R2. If you have 2 vectors in R2 and they're in different directions and ask what's the span, that would then be a plane. And then if you think about it, it has to be then all of R2, right? Makes sense? It's a little hard to understand if you go to R4. If you have 2 vectors in R4 and they're different directions, and you ask what's their span, it would be the hyperplane. It'd be kind of a plane. So, but you hopefully understand what it means intuitively in R2 and R3. Now that's not really enough. I'd like to have not only that, I'd like to know, well, what is a algebraic way? What's the general equation of this particular plane? Doing so is not difficult at all. One way to do it is to cheat and to use things outside the course. All we need is a vector that's normal to both these two vectors. Once I have that, I'll have a normal vector for the plane. I'll have a vector that's on the plane. I can then write down the equation of the plane using the normal form of the plane. But we can't do that because that particular operation is called the cross product, and it's completely not needed for linear algebra. I mean, you never use it ever. It's not in any way needed. In fact, using it actually in some way harms you because you should be using other things in order to get familiar with those other topics. So let's just tackle a different way. All that equation says is that the vector xyz is a linear combination of those two vectors. That means by our best friend, the theorem 2.4, that the system corresponding to the following augmented matrix is consistent. So then let's just row reduce that. So I'll do this by hand. So if you just take R3 and add to it R1, you get that matrix. If you then take R3 and add to it R2, you will then get that matrix. And that's enough, right? All I need is this. Because if I know that the matrix is consistent, then there cannot be a leading entry in the constant column. So the very last equation, x plus y plus z, that cannot be non-zero. It is therefore 0. And that's it. That would then be the equation of that particular plane.